my pleasure to welcome on stage Emanuel Seemann, who studied in Zurich mathematics and is now working for a French company on using AI for defense. And I think with this, you can tell us all the rest. Emanuel, thank you for being there.
Thank you. Thank you. All right. So yes, I'm Emanuel. I'm from Zurich. I'm 26. So because the guys talked today about Swiss skills, I'm apparently already a senior person. So that's really good. But yes, so today I'm going to talk about some research that we did, which is unnatural language processing, defensive AI in practice. We talk about mages, monkeys, bananas, and leopards, just to keep it interesting for you guys. We're very animal-themed company, so our logo is a bunch of alpacas. So we really like the animals here. So first, I'm going to just give you a quick rundown of who we are. It won't really matter for the talk, but so you have some context. So we're a French startup founded in 2020. You can imagine what was in 2020. So it's a remote startup. We have no office. We have a briefcase in Paris, and that's it. And we're 35 people distributed more or less over Europe. I myself have been there for a bit more than 2 years. So I'm already kind of an old hat in the company, which is also kind of funny because I'm still quite young. And we produce an open source IDPS WEF, so this is intrusion prevention system and a web application firewall. And my job is to do anything that involves AI in the company, more or less. So first, why are we doing this project? So if you have any kind of security software, this is basically how it works. So you will have some lightweight agent that reads your logs or traffic. So this is, for instance, our software works this way, but also your antivirus in your computer will read some kind of log, sometimes also the memory or something like this. And these logs, this traffic, is matched with rule sets signatures. So for web traffic, we have regex matches that we run, for instance, for the antivirus in your computer. It sometimes hashes files and then checks if this is known bad software or not. And then the detected intruders are sent to remediation, which is also a very general term for what happens. So you can imagine this might be a block at your firewall. This might be alerting your security team, and so on. So this is just general term for something general that happens. Right. And because words are kind of boring, so we have this funny slide, which is basically this whole process that you can think about. So there's a log parser, this guy that parses your traffic, that analyzes your logs. And then he sends all this to specialized wizards, mages, who are trained to detect some very specific attack. Right? For instance, the top one is the SH brute force guy. So he will detect brute force attempts. So someone trying the password on your secure shell all the time is something this guy is an expert on. Right? The middle one, this is log for shell. It's a very famous exploit in jQuery. And the bottom one is path traversal. This is a more generic scenario. It doesn't really matter what these are. It's just examples of what could be a mage. Right? And this is then, they make decisions. They say, yeah, this log line, it matches with my rules. And they send it to the remediation component, who then remediates. So maybe security team, maybe just a block at the firewall. Doesn't really matter what you do, right? It's your risk profile that matters. So this turns into a question of who teaches these mages to read. Like, how does a mage know, this is a new attack that I'm detecting, right? So if a new exploit comes out, you might have this problem where there is not really a mage readily available. So your security team has to run and basically do this work by hand, by themselves. And as a security vendor, you have to very quickly, rapidly provide such a mage for a novel exploit. So this is the update problem that we talk about here. So for a security tool to be effective, the detection signatures need to be updated continually and in a timely manner. This, of course, incurs a cost on our side. We need to have staff that is basically writing rules all the time, that is checking to see if something new was released, some new 0-day. Or it also incurs costs on the customer side. There's, I think, a very famous company that has a similar name to us that kind of taught this one trick to a lot of people. So there is some software that needs to be updated continually, and it runs on your stack, and you cannot say, oh yeah, I take the database offline, I upgrade it, I do it again. No, it needs to run all the time, right? On the other hand, so let's look at this log. This is a log I invented. We're some shoe store, right? You can read this as what kind of URLs they're hitting on your page. And you can think of this as one user's story, right? So he goes to a blog, the new Air Jordan is here. This is a shoe, a very famous Nike shoe. I'm not a shoe guy, but if you're a shoe guy, this is something you know, I guess. And then he goes on to home. He goes into search, queries Air Jordan, which seems like a typo. He corrects the typo. And then he does some weird stuff here, where he goes, Jinja, DBG, 4 name, Java, long runtime. It cuts off. You can imagine, something weird is happening here. And then he goes and buys 12 shoes and goes to checkout, right? And I think we can all agree that this looks weird and is probably not supposed to be like this, right? I mean, it's also weird to buy 12 shoes, but what can you do, right? They really like these Air Jordans. So if we had a monkey that would read all your logs, it could detect attacks by simply reporting anything that looks abnormal. So anything that looks out of the usual, right? Everyone who's going to make a search query, it's going to look like this. They have different terms, but it's going to be search, query, something, right? It's not going to be Jinja debug string, right? And definitely not Java long runtime. So anything that looks abnormal should be reported. And if we had this monkey, then we could automatically adapt to new attacks, because any new attack will just look like an abnormal string here. So this is a very, very good use case for an AI, because we can replace this monkey with an AI, and then we actually have this as a process. So this is the plan, or at least this was the plan at the beginning of this project, is we have the log parser, we have this magic AI monkey in the middle, and then he can talk to the remediation component, and this will act as a first line of defense against novel threats. This reduces our cost, because we don't have to write or have an on-call rotation to write signatures. And on the other side, for the customer, this doesn't change, right? The AI is static on your device, so there's no update that needs to run or worry about. Yes. So the questions going into this project was really does this even exist? Which would be nice, right? And then can we transfer these monkeys, or do we have to train one per customer, right? Your URL structure might look different than the next guy's web server. And this is an interesting question. Can we actually do this in a general manner? Because else, if we train one per customer, our costs scale with the number of customers instead of with the number of exploits. Still the same business problem, right? And the third one is, are these monkeys cost effective for the customer? So can they afford to run them? Is it a lot more expensive than running regex rules and matching signatures, right? So, and here there's some trick that actually researchers have developed. So URIs, this is the thing we saw before, which is basically in your URL, you cut off the first part, so you cut off the google.com or whatever. This is a URI. They have a known structure because they're created by humans. And so we can turn them into something that looks like an English sentence. And then we just basically copy the tricks from natural language processing, which is a very famous field where a lot of researchers work on. So we have a big basis of project and ideas to try. And let's run through an example here. So we have this log file, the guy searching for his shoes, right? And then we can split on what's called URL structure tokens. So this is the slash, this is the question mark. There's some more, the equal sign, for instance, right? And then it already quite looks like an English sentence. We have this percentage 20, and this is called the URL encoding. These are just structural terms because we cannot do a blank space into a URL string. So we can also recognize these and split them out. And then we have something, store, search, query, Air Jordan. You can imagine it's not the perfect English sentence. There's some stuff missing. But yeah, it's quite near to English. And if you think about the Java lang thing that we had before, that's probably going to look like a not very English string. Right. And so this is the method that was developed. It's called sec2vec. It's based on a paper by Gniewkowski. And it's basically this two-step process. So it turns the URI into a vector. This is called an embedding in the language of natural language processing. It's a very big step. I just put it in one small box, but there's a lot of effort required to do this. And then it runs a second machine learning model to like classify embeddings into good and bad. And this very standard architecture, for instance, if you do RAG, right, retrieval augmented generation, like talk to your PDF, it will use embeddings, and it will then search for embeddings on a thing. So the second model there would be a vector search. Right. And this is how the pipeline looks. This is the last technical slide, I think. So afterwards, you're going to have some fun. We first turn it into an English sentence. We turn the English into a sequence of numbers. This is called the tokenizer step. And then we turn the sequence of numbers into a vector. This is an embedding. This has bounded dimension. And then we can put our classifier model on it. This is the second model. Right. So these are the results. So this is called the val epoch loss, is validation loss per epoch. Epoch is like a training step of the model. So, and you can see it's decreasing, so it's learning something. This is very good. And it's actually quite low in some sense. 0.04 is quite good. And it gets there quite fast. Another thing is, this was work done by our intern, Federico, who now does a PhD in Italy. But what he figured out very clearly is this only works on research data. So we had this issue where we took a model that we trained, we reproduced the work of sec2vec, right? And then we just put it on a log that we actually had at our company, and it was like really bad. It would flag a lot of stuff unnecessarily, which is something you don't want, right? You don't want your customers getting blocked. And on the other side, it didn't generalize to any new exploit, right? And so this is the data problem in research. So due to various constraints like legal, privacy, you can imagine the logs that are publicly available to researchers are terrible. So they're synthetic data usually, but also like universities sometimes use their own logs, but they're not allowed to publish them because they cannot give out IPs of people for free because it's personally identifiable data, right? And in fact, this is so bad that there was a paper published this year that said, like, guys, these benchmark data sets are like, we should stop using them. And this NIDS here is a network intrusion detection systems. This is the research term for what we're doing here, right? And now this is a problem for researchers. It's not really a problem for us, because as a startup, you have customers, and or at least you hope you have customers. We do, and these customers are usually very enthusiastic about new technology, which is why they're your customers in the first place. So what we could do is we kind of contacted them, and we're like, guys, just give us some logs. We have some funny new thing that we want to try, and our CTO had to sign NDAs beyond belief, but we actually got a lot of customer logs. And then, as it turns out, on better data, these models performed significantly better. So what we did as a test to kind of find new vulnerabilities into the data set, we used nuclei templates. This is an open source vulnerability scanner, and we just kind of harvested all their attacks and then compared them to this AI model and told it, tell us, is this a bad thing? And usually it would be quite correct. All right, so the new models, they generalize to new attacks, which is the first thing we wanted to achieve. And they also generalize better to new URL structures, because we used different customer data, so multiple customers, they all have different servers and how they organize their URLs. So it would kind of learn not only like to detect the attacks on one attacker, but to serve multiple customers, right? So the conclusions, this is the first conclusion set, because I think we have more time. Yes, let's go. So the conclusions at first are like the researchers have pretty good ideas. So the model architecture, we didn't need to change much to make it work on actual data. They just have access to really bad data. So if some of you ever get asked by like universities to provide some logs or to provide something, please think of them, right? They really need some better data. And with better data, then these language models actually have serious potential in network defense. So, but the fourth point, which is kind of hidden yet, is something we need to talk about, which is performance. So in security, there is a trade-off between efficient security and kind of efficient websites from a user perspective, right? So imagine we have a standard website service or shoe store with some form of software security attached. And now there is two ways to kind of do security on this stack. So two modes. This is called the in-band and out-of-band mode. So let's bring back the mages. So this is the in-band system would be to have a user, and then he talks first to the security software. The security software wets him and sends him to our server, right? For instance, if you have a login prompt, this is an in-band system, right? You need to first pass the login system, and then you get to see the content. All right. And then the second one is the out-of-band system. Now, this is not the perfect architecture diagram. But it should get the point across, right? So the idea is the user can talk to the server before the security system has finished wetting him. And so you might ask yourself, isn't this a problem, right? There's some attacker coming in, and he can already deploy the attack on our server, and then at some point the security system is going to be like, this guy is hacking, right? And it's too late. The attack already happened, right? So if out-of-band is so insecure, why would anyone use out-of-band security, right? And the trade-off is this. So there is this trade-off on how secure a system is versus how useful it is. If you request a password, basically from the user on every action he takes, you will probably only get authenticated requests, but you might as well not get any because the user is like, yeah, nah, I'm buying my shoes somewhere else, right? And it's not really this curve, right? So there's hopefully systems that are very secure and very useful, but you can imagine that there's like some central trade-off in how much security you build in versus how useful to the user your system is, right? And so this is the performance consideration here. So a user will see a higher time to first byte in an in-band system. And time to first byte is like for instance, for an e-commerce store is super, super important. This is Google indexes this and punishes your website based on the time to first byte. So if you're not fast enough, you get deranked in Google and your sales will be very angry at this. And in an out-of-band system, the attacker might get in before the security system has time. And then in ML models, you kind of have to worry about the same thing. So we have this, what we call the deep learning trade-off, is how fast your model is versus how good the model performs. You can have very small, very fast models, but they're not going to perform as well, hopefully, again, general terms, as a good, deep, long model would. You can also call this the monkey-leopard trade-off, right? So a really fast model that's kind of stupid would be more like a leopard, and a really slow model that is really good would be more like a monkey. It's quite smart, right? So in big ML models, like monkeys, usually we use specialized hardware to run them and to train them. And this is a big cost factor, especially if you're using a security tool, right? So imagine you're some shoe store, and then your security team comes in and is like, yeah, we're going to need a big graphics card on your web server to run our security model. Like, that's just not going to work. They're never going to give you the budget for this. And there's some optimizations that can be done, and our team, Mathieu and David, they did a lot of this stuff. It's like quantization, decreasing the model size. You can do some distillation also. There's a lot of terms to train like smaller, faster models, but that are at some point less efficient at making decisions. Right. So these are the real conclusions, that researchers in general have pretty good ideas. They have pretty bad data, but with better data, their research is actually really valuable for defense. But the feasibility of running big ML models is still an open question, and we're kind of going to see if this is going to work out or not. Because what we're doing, we're an open source company, right? So we're going to open source this. So the answers coming out of the project is, does this famed AI monkey even exist? Yes, it does. We've shown this, we've seen this. Can we transfer the monkeys? Yes, if we feed them enough and diverse enough bananas, right? We need to feed them enough data. We need to have a diverse enough training set that this URL structure from one server doesn't really poison the generalizability of the model. And are they cost effective? No, but we can train leopards instead and hope for the best, right? And so what we're doing at CrowdSec is we're going to open source these models. We're going to open source the plugin that can be used to run Sec2Vec. It's soonish. It's Q4, Q1. We don't know yet. There's a lot of problems you can imagine with like packaging and runtime and so on. For the people that don't know us, this is our repo for the main product. And it will be a branch on there. And if you have any interesting things to contact or ask us about, you can go datascience@crowdsec.net or my personal email, which is Emanuel@crowdsec.net. Thank you for listening. And are there any questions?
Thank you, Manuel. And have an applause. Yes, are there questions? There's two. We start with the guy in the back.
Thank you for the talk, very interesting. So I have one question about the initial motivation, I think was about anomaly detection, but then the way it was presented, it looks like more classification. Is that the case?
Yes, that is the case. So it is a classification problem. The anomaly detection use case we tried at first, so scroll back. The whole project was set out as an anomaly detection project. But we figured out along the way that anomaly detection systems, they are too slow to react because they kind of need to save the state of what is not an anomaly. And if you kind of do these fetches to like whatever you use to hold this state, it will be too slow to work. And so the project is still called the Anomaly Detection Project, but what we are actually doing is classification, yes.
Thank you.
Thank you. We have a second question in the third row.
Thank you for your talk. I have a question. Did you try to combine the kind of old school way of statically discover attacks with the ML way you presented now?
So the implementation is actually more or less going to do this. So how we're going to put it is the model will evaluate the line, and then it will give you a percentage of confidence that it thinks this is bad. And then the idea is like the way configuration works in CrowdSec is you have a big YAML file for each scenario where you define what to match, what to do. And the idea is, at least in our head, how people are going to use it is they're going to use this confidence to kind of inform the next step of matching rules that they're going to do. So, for instance, if you do a SQL injection, right, you look for terms like select, whatever, $1 and so on, and you can match for these. But if, depending on how your web server is configured, this might get a lot of false positives. But if you kind of put the anomaly detection framework in before this, and you say, if it's detected as an anomaly by the AI system, and we match some kind of SQL injection terms, then we send it to remediation. So this would be kind of the idea of how you're going to use it. Because also, like, the image I painted before of this being a really good system is accurate, but it's not perfect. And especially when you're starting to block real customers, you kind of want another filter before this automated system. Yeah.
Thank you.
Thank you. We have time for one more question. Yes.
You mentioned you had or you needed lots of actual logs from customer. Did you got it labeled somehow to train the model, or how did it work?
So we labeled a lot of it, and some of them was labeled by the customer. So they would send us basically what they had in their whatever security, CMs, or you get the point. Yes. Some of it was manual labor done by us, mostly our internal, you know. But yes, there was manual labor involved.
Can you tell us something about the cost for learning? Because I really like the trade-offs that you were making, like pace versus quality. Now, you can really have the trade-off in that you shift a lot of the burden to the moment before there is an actual request to the web server, right, to speed things up. It's like with electric vehicle mobility, right? With electric vehicles, we don't know where the CO2 footprint is. It's somewhere, I don't know where this is, manufactured, the batteries and all the ingredients. But while the car is on the road, there's no emission, right? So in the similar way, what you're doing here is that the web server, once it gets the request, is very, very fast. But still, there's a lot of work to be done for the training. Now, can you tell us the effort for the training that is happening before it comes to actual requests against the web server?
The trade-off in so the model size impacts the cost of training as well. So this is it's not really the more you pay up front, the less you have to pay after. But it's in some sense you can pay a lot up front and then you also have to pay a lot after. So there are, as you say, there is, of course, an advantage to letting it run longer, and we are experimenting with how long we should run this in training. But again, like the big trade-off will impact both training and inference of the model.
For sure, but can you tell us like how much effort you spend for the training part? Like how much does it cost you in terms of money, in terms of resources, etc.?
Good bit of AWS credits, yes. So I cannot say you a number, but the instances cost a bit for GPUs, and we have some optimizations done by Mathieu, who optimizes the training a bit. But I cannot give you a number on this, I'm sorry.
Okay, so thanks again, Emanuel. Thanks for the talk.